So hello everyone, welcome back to Hasmora Education. Today will be solving another paper of physics theory, which will be May June 2024, paper 2, variant 3 or QP23. So time allowed for this paper is 1 hour 15 minutes. So without wasting any time, let's begin. So question number 1 says the drag force Fd acting on a sphere falling through a liquid is given by Fd is equals to 6 pi and Rv, where R is the radius of the sphere, V is the speed of the sphere in the liquid, and N is the property of a liquid called the viscosity. So now what are we going to be showing is the SI base units of viscosity are kg meter per second. So as we know that any type of force is equals to, it can be F is equals to ma, which is kg meter per second minus 2. The kg because of the mass and ms minus 2 because of the acceleration, and the speed is equals to meter per second. So the 6 pi will be neglected. Why? Because it has no units and it is a constant. So 6 pi will be ignored, while the radius is actually is equals to meter, the speed is equals to meters per second. So now let's make the viscosity the subject. So viscosity is equals to Fd divided by Rv. So kg meter per second minus 2 divided by meter per second into meter. So this becomes kg m s minus 2 divided by m square s minus 1. So this gives us s minus 1 and this gives us minus 1. So it becomes kg m minus 1 s minus 1. So hence we have shown the SI base units of the viscosity are kg, m minus 1 and s minus 1. So now the B part says the sphere has a radius of 3 cm and falling vertically downward at a terminal velocity of 2 meter per second through a liquid. The drag force acting on the sphere is 0.096. So the Fd is equals to 0.096, which they have already told us. So now we have to calculate the viscosity. So in this case, the equation is going to be viscosity is equals to Fd divided by 6 pi Rv, and this becomes 0.096 6 pi into R, as it is in the centimeters, so we have to convert it into meters, and then the speed, which is 2 meters per second. So now let's calculate this. 6 pi into 3 into 10 power minus 2, 3 into 10 power minus 2 into 2 into 6 pi, and 0.096 divided by this, so it becomes 0.08488. We will write it to two significant figures as the raw data is being provided in two significant figures, so it becomes 0.85. So now the the C part says the sphere is shown in the figure 1.1. On the figure 1.1, draw and label The arrows to represent the direction of the three forces that are acting on the sphere as it falls at a terminal velocity through the liquid. So one of the forces, as we know, that will be acting on it from the center is for sure the weight of the sphere. As it is moving through the liquid, there will be a drag force on it, which we will call the Fd, and there will also be an upthrust called the F up. So these were the three forces that will be acting on the sphere as it falls through the liquid. As it is moving at a terminal velocity, that's why we have to keep the magnitude of the lines equal so that the drag force and the upthrust is equal to the weight, which ensures that it moves at a terminal velocity. The part D says the density of the liquid is 920 kg meter cube, show that the upthrust acting on the sphere is 1 Newton. So the upthrust formula is rho GV, where rho is the density of the liquid, 920 into the acceleration of the free fall, and into the volume. The volume of the sphere is 4 by 3 pi r cube. So r is 3 centimeter or 3 10 power minus 2. So this becomes 9.81 into 920 into 4 by 3 pi into 3 into 10 power minus 2 and cubed. So this gives us the answer 920 into 9.81 into 4 by 3, 4 divided by 3, and 3 into 10 power minus 2, and this is whole cubed. So now let's check the answer. So this gives us the answer of 1.0, 1.0207. So rounded off to two significant figures, it becomes 1.0 Newton. Now they are telling us to calculate the mass of the sphere. So many people will think here that we are going to be using density is equals to mass divided by volume, but they have not given us a density of the material, which will lead to confusion. So what are we going to be using? As it is moving to a terminal velocity, we know that the weight of the sphere will be equal to the drag force plus the upthrust force. So this is how we are going to be finding the weight and then the mass. So weight is equal to the drag 0.096, which they have given us initially, and the 1 Newton. So it becomes essentially 1.096 weight. So the mass will be 1.096 divided by 9.81, which gives us 0.11 kg mass. So this will be the mass of the sphere. The second question is define displacement from a point. So when it comes to definitions, I told you you have to be very specific in answering these questions. So displacement is defined as the shortest distance covered in a specified linear direction. Or you can also say that from a fixed point of reference. An object is projected horizontally at a speed of 6 meters per second from a slope as shown in figure 2.1. The slope is at angle theta to the horizontal. Air resistance is negligible. So let's highlight that point. So the air resistance is actually negligible and the angle is theta. The object lands on the slope at a time of 0.71 second later and stops without rolling or bouncing. So determine the horizontal distance. So what can we actually see is that it is a type of a projectile motion. Like for example, this is released in the form like this, and it does not bounces further. So it has the horizontal component of the speed, which is 6 meter per second initially. So whenever it comes to the horizontal component, we just use the equation speed is equal to displacement divided by time, distance divided by time. So it will be equal to at distance is equals to speed into time, as they have given us the speed as well as the time. So it becomes 0.71 into the speed, which was 6 meter per second. So 0.71 into 6 meter per second comes out to be 4.26 meters. So rounded off to two significant figures, it becomes 4.3. Now they are telling us to calculate the vertical distance traveled by the object. So as the object is traveling through the gravity, and the the vertical component of the speed is 0, so it will be 0. We do not know the distance, and the gravity is the acceleration, which will be positive as it's moving downwards. So the initial is 0, so it becomes S is equals to ut plus half at square. As we know that the time is universal for both directions, we can use it in both directions. So it is 0 into 0.71, or you can simply ignore it. So this is the equation that actually forms. So 9.81 divided by 2 into 0.71 square, so it becomes 2.47, which rounded out to 2 significantly becomes 2.5 meters. So now the third part says use the answer in B1 and B2 to calculate the theta. So now how are we going to be calculating the theta? Let's move to the diagram that we are provided with. So we just calculated the vertical distance, the distance V, and the distance horizontally. So this can easily be used to calculate the theta here. So now let's calculate this. For example, this was the triangle. Okay, so this was the triangle. This is theta. This was the vertical distance, which was, I believe, 4.3. And sorry, this was not 4.3. The horizontal distance was 4.3. This was 2. This was 2.5, and this was 4.3. So now we can use tan theta. So tan inverse will be equal to 2.5 over 4.3, which gives us 30.17. So round out to two significant figures, it becomes 30 degrees. Determine the magnitude of displacement of the object from its original position. So displacement in the shortest path. We have just used a triangle which was like this. So this is 2.5, this is 4.3, and this is the h. So h square is equals to 4.3 square plus 2.455 square, which you have studied in Pythagoras theorem. So this becomes 4.3 square plus 2.5 square, and then under root it to find the h. So it becomes 4.97 meters. So you can write it as 5.0 meters to two significant figures. Now they are telling us by considering the energy, calculate the speed of the object before it lands. So now we have calculated the speed of the object before it lands. So now we know that it has traveled a vertical distance of 2.5 meters. But there are also kinetic energies involved. It has a kinetic energy due to the 6 meter per second. When it was at the start, it was projected with 6 meter per second. So we will say that the change in kinetic energy will actually be equal to change in the GPE. So half m and then v square minus u square. We do not know the final speed, that's what are we actually looking for, and mg delta h. We don't know the mass since it will cut out, and half into v square minus 6 square, which will be equal to 9.81 into 2.5. So this comes out to be v square minus 36 equals to 9.81 into 2.5 into 2. V square is equals to 9. Let's calculate this and simplify it. So it comes out to be 49.05 and plus 36. So this comes out to be, just add the both and then underroot it. So we'll be underrooting the answers on the both sides. It comes out to be 9.22, or you can write it to two significant as 9.2 meters per second. The third question says states state the Hooke's law. So what we actually know about Hooke's law? Hooke's law is the you can say the proportional relationship between the extension and the force that are being applied on the body, an elastic body. So we will say that the extension produced in the body is directly proportional to the force applied till limit of proportionality. So this was the answer for this. B part says the variation of the applied force with the extension for the sample of the material shown is in the figure 3.1. The sample behaves elastically up to the extension of 80 millimeters and breaks at the point X. So on the line, draw a cross to show the limit of proportionality. Label this with the letter P, and then the second part says draw a cross to show the elastic limit and show this with the letter E. So we know the limit of proportionality is the point till when the object has the graph has a straight line, like you can say this point, and after the elastic limit, it actually starts to deform. And they have told us the elastic limit which is at 80 meters. So we will just draw across here and draw across here. Just let me increase the width of this. This will be the 2 points. This will be P and this will be E. So we have drawn the 2 points. So now further they are saying us the sample in the B has a cross-sectional area of 0.40 millimeter cube. So let's just first convert this into meters. 0.4 as millimeter square. So we have to square the 10 power minus 3, and the initial length is actually 3.2. For the deformation with the limit of proportionality of the sample, determine the spring constant. So the spring constant is actually is equals to F is equals to KE. So K is equals to F over, you can say F over X or F over E. So let's find out at any point within the limit of proportionality. So let's just take this peak point. This will be 5. This becomes 5.2, 5.4, so and 5.6. This is 5.6 and this becomes the, let's just take it here. This is 5.4 and this is 50, not 50. If there is a difference of 40, so it will become 60 millimeters. So the force is 5.4 and divided by 60 into 10 power minus 3. So this comes out to be 5.4 divided by 60 into 10 power minus 3. This comes out to be 90. Now in the second part they are telling us to find the Young modulus of the material from which the sample is made. So we know that the Young modulus is actually equals to the stress over the strain. So now stress, just open the formula F over A and into delta L under L. So we know the cross-sectional area. We also know the force to the point. We can just use the spring constant. For example, this is actually the spring constant. This is F over X, the change in length under the force. So we can just use this. So this is 90 into the original length. This is 3.2 and the cross-sectional area we have found out to be 0.4 10 power minus 6. It becomes minus 6. So this comes out to be 90 into 3.2 divided by zero point 0.4 into 10 power, so 10 power minus 6. This comes out to be 7.2 into 10 power 8. So this is the Young modulus of the material. In the D part, they are telling us determine the estimate of the work done on the sample as it is extended from the zero extension to its breaking point. So we know that the work done is the area under the graph, but what's the twist here is that the graph is non-uniform to a certain point. The graph is uniform till the limit of proportionality like this point, and also for this point. Graph is uniform till here. So what we can do is that we can just calculate this first. So let's calculate this distance. This is the point till here. This is this point. So it is actually, just let me calculate the difference between the big rectangle. So it is 60 at one end and at the second end it will become 180 plus, so actually it will be 192. It will become 192. So 192 minus 60 into 5.4. Now let's calculate it step by step. So it will be the area of triangle plus rectangle. This will become half f into x, which will become 5.4 into 60 10 power minus 3, and plus the rectangle, which will be 5.4 and then into 60 192 minus 60 into 10 power minus 3. So, and then also we have to add the small boxes. So let's find out the area of one small box here. So as we know that the one big box is equally divided into 40 millimeters, so let's divide it by 10, so it becomes 4 millimeter. So actually one small box is equal to 4 millimeters from the x-axis, 4 millimeter, and on the y-axis it becomes zero point 0.2 meter. So now let's calculate the number of the boxes here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, and 52. 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, and I have missed one layer here. 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 4, 85, 86, 87, 88, 89, 90, 91, 92, 93, 4, 95, 96, 97, 98, 99, 100, 1, 2, 3, 4, 5, and 6. So it is 106 boxes. So now I have taken the two partial boxes as one box just to maintain the accuracy. So I've counted off to 106 boxes, and it is 4 into 10 power minus 3 4 millimeter into 0.2. So this comes out to be, let's calculate it as a whole. So 5.4 divided by 2 into 60 into 10 power minus 3. This comes out to be 0.162 plus 192 into 10 power minus 3 minus 16 into 10 power minus 3 into 5.4. This comes out to be 0.7128 plus 4 into 10 power minus 3 into zero point 0.2 into 106. So it comes out to be 0.0848, and let's just sum it. So it comes out to be 0.9596. So just round it off to two significant figure, it becomes 0.96 joules. So it was a complex one. So just let's move to the another question. So in the next part it is saying that a second sample of the same length, same material has a larger cross-sectional area. The cross-sectional area is increased and then the original one, and but the same initial length. The two samples are each defined with the limit of proportionality. So you can explain qualitatively, like we do not have to use any of the numerical values, how the spin constant of the second samples compare with the of the original sample. So I have told you the Young modulus is actually equals to K into L divided by the A. So just rearrange it. So Young modulus into the area into K into L. So this is same as the same material. So when this is increased, this will automatically increase. So we can write here as the spring constant is directly proportional to K to the area, the cross section area. Hence, increasing cross sectional area will increase the spring constant. So second sample has larger spring constant. So we are done with this question. So the next question says a progressive transverse wave traveling from right to left to right is shown at an instant in the time in figure 4.1. So R and T are the points on the wave state, the phase difference between R and T. So I can clearly say that this is the one wavelength. Okay, this is the one wavelength from the crust to crust. It is the one wavelength. So this is quarter wavelength, this is another quarter, and this is another quarter. So 0.25 into 3 becomes 0.75 lambda. So we have the formula delta x over lambda into 360. So I can say that it is 0.75 lambda divided by lambda, as they have not given us any distance. So I'm going to be going with that. So it comes out to be 270 degrees. On the figure 4.1, draw a point arrow at the point T to show the direction of the movement at point T at the instant shown. So as we know, and you must remember that whenever there is a decreasing gradient here like this, so at this point the the particle has to move up on the instant, and where it is an increasing gradient, the particle has to move down. So let's just clear the and let's draw it here. So this is going to be moving, sorry, not up, it is going to be moving down, as it has a positive gradient. So this is the movement at the instant. Okay, now they are telling that the horizontal distance between R and T is 0.62 centimeter. So the speed of the wave is 0.27. Calculate the frequency. So I have already told you that it is 3 by 4 lambda is equals to 0.62. So the lambda comes out to be, just calculate it first, into 4 divided by 3 comes out to be 0.62 into 4 divided by 3. So it is coming out to be 0.827. So the frequency f lambda is equals to v. So 0.27 divided by the lambda 0.827, and then it will be become equal to the frequency. Frequency comes out to be 0.27 divided by 0.827. So it will come out to be 0.33. Okay, I have done a mistake here. It is not the it is not it is 0.62 into 10 power minus 2, because there was centimeter there. I just didn't uh, observe it. So it will become 0.827 into 10 power minus 2, and then 0.27 divided by 0.827 10 power minus 2. So it becomes 32.6 hertz, which will be essentially 33 hertz rounded off two significant figures. So just be very careful when you are dealing with the units. The part D says the water in the water wave produced by dipper S1 attached to the vibrator in the dipple tank. An identical dipper S2 is attached to the same vibrator. The two dippers produce an interference pattern. So the identical dipper is used because they are in the constant, they are coherent to each other, and they can um, actually they can interfere with each other. So the wave crests from the each source are represented by the solid lines of the figure 4.3, and the wave troughs are represented by the dashed lines. You should also memorize this point, that the crests are shown with the with the solid lines always. And for example, if there is like a circle like this, so you have to recognize that these 2 points are actually the crust, and the middle part will actually be the trough of the wave. So now let's continue it. So the at the point P in the figure 4.3, the wave from the S1 has the same amplitude A as the wave from the S2. So it describe and explain the amplitude of the resultant wave at point P. So we can clearly see that the trough and the crust are actually coinciding on the point P, which will result in a destructive interference of the two waves, resulting in the less resultant displacement. So we can write here as the crust and trough of two waves superpose the two waves are out of phase, resulting in no resultant displacement. Hence, due to the destructive interference, the displacement at P will always be zero. So this is the answer for this. The question number 5 says change the Kirchhoff's second law. So at this point you should actually have this thing in your mind that the sum of PDs, sum of EMF is equal to the sum of individual PDs across a closed loop. Second part says state a conversion law that gives rise to the Kirchhoff's second law. So we have studied that the first law is based on the conservation of the charge, and second law is based on the law of conservation of energy. B part says a circuit contains a cell of internal resistance R and two resistors R1, R2 as shown. So the potential difference across the two resistors is V, which is being parallelly connected to the parallel components of the resistor. The current is the cell is I. So use Kirchhoff laws to show the total resistance RT of the external circuit is given by the equation of the parallel or the parallel combination of the resistors. So in this derivation we actually use the both of the laws of the Kirchhoff. So the Kirchhoff first law says first law says actually the current is not same as the parallel component is also involved. So the total current is actually equal to the drop in R1 and also in R2. So what is the formula for what can the how can the current be actually broken down? So V is equals to IR, so I is equals to V over R. So we can write it V over RT is equals to V over R1 and plus V over R2. So now we actually know the sum of the PD is actually equal in the parallel across each of the wire. So we can just take it as common, and V into 1 over R1 and plus V into 1 over R2. So the V actually cancels out, and this gives us the formula 1 over RT is equals to 1 over R1 plus 1 over R2. So we have derived it correctly. The second part says the electromotive force of the EMF is 1.5. The values of R1 and R2 are 10 and 15 respectively. The PD measured by the voltmeter is 1.3 V. Calculate the internal resistance of the cell. So now let's get back to it. So one of this was 15 ohm and one of this was 10 ohm. Okay. So and the the EMF of this is actually 1.5 volt, and the PD that is actually being received in the terminal path is the 1.38 volt. So what it actually means, how can we calculate the internal resistance? So first of all, what we can actually do is that we have to combine these both resistors. So let's just find the total resistance. It will be 1 over 10 plus 1 over 15, and then we have to inverse it. Okay, so this becomes 1 divided by 10 plus 1 divided by 15. So this becomes and 1 over 6, and which is inverse to form 6 ohms of the 6 ohms of the resistance. So this component is actually equal to 6 ohms. We can just draw it as a single component. This is equal to 6 ohms, and the current can be calculated as we have the potential difference here is 1.38. V is equals to IR. 1.38 is equals to I, and the R can be shifted at the other side, 6. So I is it comes out to be 1.38 divided by 6. So this comes out to be 0.23 amps. So we have found out the current. We know the lost volts. 1.5 minus 1.38 comes out to be 0.12, I believe, and 0.12 is equals to IR. So this divided by the 0.23 is equal to the internal resistance. 0.12 divided by the current comes out to be 0.5217. So this is 0.52 ohms, correct to two significant figures. So we have found the internal resistance. This is 0.52 ohms. Okay. This part says the a third resistor is added to the parallel with the R1 and R2. So whenever the a component is added, the effective resistance decreases. Why? Because it is the reciprocal of the total resistors. So shall explain the effect if any on the change on the current in the cell. So as the total effective resistance decrease, there will be more more current in the wire. Hence the current increases. And the PD measured by the voltmeter. So as the resistance of the external circuit is decreased, there will be more current and there will be less share of PD across the both resistors. So hence there will be more share across the internal resistance. So the PD will decrease. The PD across voltmeter will decrease as the effective resistance in external circuit decrease and more share will be given, or more PD will drop to the internal resistance. So I hope this is clear. Let's move on to the next question, which is, I believe, the last one. So the nuclei of the isotope of samarium each contains 62 protons and 85 neutrons. So state a nuclear notation. Nuclear notation means writing in the form X is equals to A and this is Z. A is the mass number or the nuclear number and Z is the proton or atomic number. So let's just calculate it, just write it quickly. So this is Sm and this is 85 neutrons. So we have to add these both, 85 plus 62. So this comes out to be 147 and this comes out to be 62. So this is the nuclear notation that we have written. This isotope of samarium is radioactive and decays by emitting particles. Gamma radiation is not emitted. The energy spectrum of the emitted particles is shown. So what do actually we mean by the energy spectrum? Energy spectrum means the range of the kinetic energy of the particles. So you must have probably studied that the beta particles have a continuous range of energies. So it actually looks like this, or it can be like this. It can be anything, but it is continuous. So what we actually can see here is that it is just a straight line, which means the energy is confined and only it has only one amount, while in the beta particles it has a continuous range. It has varying amount of the energies, which is because of the you can say different proportions of the energies just to conserve the energy. So explain how figure 6.1 shows the isotope of samarium emits alpha particle and not emit beta particles. So we can write beta particles have a continuous range of energy, while figure 6.1, or you can also write it, you can also observe when a beta particle is emitted, it has short range and it is more of, you can say, scattered, while the alpha particle is confined and more thicker line, it gives more thicker lines which actually represents more energy. The figure 1 point shows only single amount of energy, or you can say it does not show varying amount of energies. The isotope of samarium decays the isotope of neodymium and give the radioactive decay equation for this decay include the nuclear and the proton number of all the particles that are being involved. So the Sm 147 62 decays by alpha particle. So this is 42 plus it forms Nd and it is 143 and 60. So this was for this part. Now in the third part they are saying that a baryon is composed of three quarks which have different flavors. The baryon has a charge of 0. Two of the quarks in the baryon are up quark and the bottom quark. Okay, the charge is 0. So we know that the up quark is plus 2 by 3e and the bottom quark is minus 1 by 3e. So what the third quark has to be? So plus 1 by 1, so plus 2 by 3 e plus 2 by 3 e and then minus 1 by 3 e plus q is equals to 0. This comes out q to be minus 1 by 3 e, or you can simply just do it by mathematically minus 1 by 3 e into 2 is minus 2 by 3 e, minus 2 by 3 plus 2 by 3 e is equals to 0. So this is minus by 3 e. So now state a possible flavor for the third quark in the baryon. So you can write any one. You can write strange. It has also minus 1 by 3 e. You can write possibly you can write the down quark, but you have to write a different one from the which has been already you can say included. So this was all for today. The paper is finished here. So I will meet you in the next video. Please like, share and subscribe the channel and share it with anyone who you think might it help. So I will meet you in the next video. Till then, goodbye.